discharge would be, so you have to control it. So typically, I mean,
but the variability of the wind blades, the turbine blades, stuff like that, that would not have to be conditioned. The output of the wind turbine.
the output, the turbine would produce you an AC voltage.
Yeah, the generator output.
The generator output, it would be typically in a wind thing, unless it would be an AC voltage. Okay, an AC voltage, you would change it to DC and charge the capacitors up there. Yeah. To charge the capacitor, you charge the DC, because the capacitor, it's a frequency-dependent device.
I didn't know what I was talking about.
If you physically look at it, it's just two plates. Picture is a square plate with a little distance in between and dielectric insulating material, and you apply. See, a capacitor, it's a frequency-dependent device. At a certain type of frequency, it would allow current to flow through. Okay. Capacitors and inductors are frequency-dependent devices. Okay. So therefore, if you charge them, you charge them as DC. The beauty about the capacitors is actually that you can charge them, they hold their charge, and then they can discharge extremely fast. Okay? And it has to be a super, but you can charge capacitors in many kilowatts. You can put it, I mean, I worked in applications that actually we charge capacitors to 60,000 volts, charge them and then discharge it. So you can, when you discharge them and you hear a bang up there, it makes this room shake. So it's pretty, and you can't discharge it with a normal switch. You have to put like an air switch or something, because otherwise it blows down. So wind turbines actually is one of the, so for the application of this, you have to either mount them extremely high or inside different locations up there that you have a wind. But this is, again, this is actually one of the methods of alternative energy. A lot of people spend a lot of development, of course, on this one. We'll talk about it in the future, okay? Fuel cells, on the other hand, again, typically, and you hear quite a bit of this, consists of a cathode and anode. Again, you separate this from electrical membrane material. It's typically what you have is an electrochemical type of a reaction that takes place. The good thing about it, some of the fuel efficiency is as much as what? 50%. So everybody gets very excited about fuel cells. And if you use some other methods up there, you can actually get it even higher than that. Typically, if you look at typical fuel cells, you're using what? Hydrogen and oxygen, and you transfer electrons from one place to the other, and the byproduct you got is water up there and heat. So it's another method that you could possibly, another type of system that you can tie it into what? Into your photovoltaic system. So all of the systems is you can have utility, PV system, and you're integrating all this stuff for additional energy. Now, why we're going through that? Because so this way we get the whole concept that it's not only the PV system that can be used. Okay. Some of the configurations that you have, and you can see it's actually the standalone, and in the standalone you have what? The direct couple of one systems. All you do is you have the array up there supplying the load, and that's about it. The only problem that you have with the only other balanced system components, you may have a disconnect up there, or you have to have what? Some mounting. No, the direct couple of them, you don't have to have any batteries up there, and they only what? When the sun is shining, the producing energy, you supply the loads. The only problem with them is what happens, you must what? Precisely calculate your load to your system. And you have to make sure that you need your load to work when the sun out. If you don't have no sun, there's nothing. So basically, the simpler ones of this is what? It's a typical array to the load. If this is 60 watts, this is 60 watts. You get 60 watts in here with certain efficiency, you get the light bulb. You don't, nothing else, okay? Then you have a self-regulating type of a standalone system, no active control, and this is an important one up here, to protect except through what? careful design. Usually for these things, what happens is you have to make sure that in this self-regulating system you don't what? Accidentally what? Burn the battery, okay? You have an array, a battery, and a load, okay? Less components, very little expensive, but you have to have what? Extremely designed to your load. What happens now if all of a sudden you're generating what? More power. You can do what? Burn the battery. So you have to put what? It's vulnerable to overcharging, okay? Or if you undercharge the battery. So usually what you do here is, typically you make sure you oversize the battery should you have a condition like that. So actually you overcharge the battery, or you really matching the voltage to a fully charged battery. So this is the only consideration. Most of the times if you have a system like that, you overcharge the battery, you oversize the battery, and then you're pretty good at it. Not that you're going to get involved with these things, but it's nice to know. This is what we call a self-regulate, the only components that you have in here. If you don't, then you can kiss the battery goodbye. Charge control systems, types you have. You put systems that actually prevent from the battery being charged or overcharged. You provide some sort of what? Limiting method to the charge current to a fully charged battery to prevent this thing from what? From overcharging. Or sometimes if you have a system like this, standalone system that you're generating more, what you're doing is you're twisting some auxiliary load on, so this way it can go on. So if you look at it, and usually, because the code, because the code requires that anything, the charge code is required by the NEC if you have an array that is what? That the current is equal to what? 3% or more of the rated battery capacity in ampere hours. So the code says, look, if you have that condition, you have to have what? Charge control. So you got to provide that. So if you have a 100 amp battery, will require charge control. The maximum rate charging current is what? 3 amp. So typically with that, what you're doing here is you put a charge control, there's your batteries, here's your loads, and then you have without load, with load control. This is without load control. Standalone systems that you have for AC loads, okay? Now what you're going to do is what? Now you have a standalone system, but you must have what? An inverter to convert the DC to what? To AC loads. And so this way you can supply DC to DC and AC for the AC, okay? Now once you do that, you have what? A conversion process, so you have to accumulate to consider some of the conversion process, so you have some losses associated with the inverter, okay? You look at this one, a typical configuration for that. This is your charge controller for the battery. Then from the battery, you take the DC to the inverter to the actual distribution panel. Okay. A lot of the times, this and this combines together, so you're left with that. Okay. Utility interactive, we talked about it. System. It operates in parallel with the utility grid. Okay. The system, most of the time, you call them interactive, or it's grid-based or utility-based. It happens to be the least expensive ones, okay, and they require the least amount of components. And you have the ones that use batteries and don't use battery. Primary component is what? The inverter, okay. Interfaces directly between the utility and your array system. They are modular, so this way you can design a 10 kW or 9 kW system by putting what? 3 kW systems together. Typically, representation of them is your utility, your inverter, your interactive inverter, right to your AC distribution panel to your meter. Net metering. Some of you have heard this word, some of you have not heard. Net metering means what? One meter that allows you what? That the utility is using. The meter spins one direction, what? When you consume it, when we actually taking power out of the utility, the other one is what? The meter spins the opposite way when what? When we actually giving power. What causes the meter to spin backwards? Think about it. What causes the meter to spin this way, and what causes it to spin the opposite way?